So we have a very distributed presentation here today. I am in Sweden, and Jörg, you are in
Mexico.
Mexico. So hopefully everything works out. But
Yes.
hi everybody. My name is Robert Hällqvist. I'm a technical fellow at Saab Aeronautics within the field of modeling and simulation. Jörg is my colleague. Jörg, do you want to introduce yourself quickly?
Yeah, as Robert said, I'm working as well at Saab as a system engineer.
Yes, and the title of our presentation here today is Aerospace Modeling Workflows for Advanced System Simulation. Hopefully what that means will become clearer throughout the presentation. I will have a set of first slides here to set some context and background and so forth, and then Jörg will talk some about modeling of flight mechanics using Modelica and System Modeler and other tools. So I will start to talk a little bit about modeling and simulation at Saab, why we are using modeling and simulation, past and present. I will use general vehicle systems as an example, as both I and Jörg work with modeling and simulation, primarily of general vehicle systems. I will talk some about what I refer to as our distributed approach to modeling and simulation. I will then speak some about our modeling and simulation application development process and provide a connection to FMI and also SSP. Yeah, you heard about FMI in the previous talk, so I'll also introduce this second standard. And then, as I mentioned, Jörg will talk some about modeling of physical systems, and then we'll round off with some summary and conclusions. So Saab Aeronautics is an aircraft developer, and this is something that we have been doing for a very long time. Here you can see some pictures of three Saab developed aircraft. We have in the top right, we have the Saab 29 Tunnan or barrel aircraft. In the middle, we have my personal, at least aesthetically, favorite aircraft, the Saab 35 Draken or Dragon. And we have the trainer aircraft, the Saab 105 at the bottom. This Draken aircraft is according to the myth or an anecdote, is that it did not have a top speed. It would simply accelerate until it ran out of fuel. Yeah, so all of these aircraft were undoubtedly very successful in their time. And even though we at our department, we usually brag about having used modeling and simulation since the 60s, we cannot claim that any of these aircraft were actually developed with extensive use of models in the loop. Today, however, we have working on different aircraft. We have the Saab Gripen aircraft in the top here. We have the Global Eye to the right. We have the T-7 Red Hawk aircraft with this red part of the aft fuselage, and then we have whatever is coming next. And here we are using modeling and simulation to a very large extent during development and also during operation. So what is different? Before pointing out what has become different, just using general vehicle systems as an example. So these are general vehicle system of which both I and Jörg work with, are aircraft subsystems that are general, that exist in both military and civil aircraft. So cooling systems, hydraulics, fuel system, etc. Nowadays, we classify also propulsion systems as a general vehicle system. Today, they typically consist of both complex hardware and software parts. They are tightly integrated with the aircraft as a whole and highly connected to one another. And each subsystem is designed to solve a number of different tasks. And this is at large one of the reasons why we need to use modeling and simulation during development in order to not only cope with emergent behavior that arise when these different subsystems interact, but also the ability to exploit them to make a better product in a safe way during development. With aircraft, we are not able to test things uh, in the aircraft and fly in the operating conditions where they are intended to use from the get-go. We need to have a safe representative environment and their models and simulations become essential. So when using models for development, we adopt a distributed approach. And with that, I mean that the models are developed by the parts of the organization that are responsible for also developing the subsystems. The engineers are spread, developing models can be spread throughout the organization, and they are prompted to use the best suited domain-specific tool at hand to develop their models. We strive to make simulations, models, and simulators available to all engineers that need them throughout all the life cycle phases. And we employ modeling and simulation on an increasing system level throughout development, ranging from component to subsystem to aircraft and systems of systems in the end. Here we have a schematic representation where I put some sort of abstract measure on the vertical axis representing level of integration. So in a sense, how many of the different subsystems that are integrated in the simulation. And on the horizontal axis, we have some abstract representation of time. And here I wrote early phases and late phases. So that does not mean that there are not even later phases here, such as operation. Or this is an undefined boundary, I should say. But if we are to work this way, then credibility assessment as an umbrella term becomes essential. So when developing a new aircraft vehicle system, we typically start by modeling the included hardware. And I myself, I am a Modelica proponent, so I would develop this model using Modelica and various different Modelica tools. But as I mentioned earlier, we strive to use the best suited tool for the task at hand. So when developing this model of the hardware, we do a lot of simulations to mature the model and to specify the hardware to be included in the subsystem and so forth. And we use this model for safety assessment, performance analysis, load analysis, etc. And here I try to indicate that we are using the model throughout the life cycle phases. In the late life cycle phases, we heard Jan talk about digital twins, and this would be a potential digital twin prototype in this early phase. So once we feel that we are this model is mature enough, we develop a corresponding controlling software, and we integrate the hardware model together with the software in what we refer to as a small-scale simulator. When I say simulator here, I mean the complete architecture, including the models, but omitting the actual simulation engine, the tool driving the simulation forward in time in case of time domain type simulation. So here we have a small-scale simulator incorporating hardware, the hardware model and the software of a single subsystem model or of a single subsystem. And we use this type of simulator for the same purposes as the hardware model, to develop the models, the software, to do safety assessment, performance analysis, etc. We run a lot of simulations, and once we're mature here, Maybe we develop a mid-scale simulator where we incorporate several different closely related subsystem models and their corresponding software. And this we use, for example, for architecture evaluation on a higher system level and a more holistic performance analysis. And lastly, we go to our large-scale simulators. These include most of the model aircraft subsystems. We have an ambition to be flexible here. We have full desktop type large-scale simulators, as well as hardware-in-the-loop simulators. These type of simulators are typically used by pilots and a number of different of the subsystem developers. And they are also shipped as products for training purposes, etc. But in-house at Saab, we use them typically for integration testing, fault analysis, and evaluation of the behavior of the complete aircraft. So with this very distributed approach, we need to have tools, methods, and processes to enable efficient reuse of all the digital artifacts that go into these different simulators. Some of the strengths are that the subject matter experts have direct input on every digital artifact, and all of these subject matter experts are typically dispersed throughout the organization. So this distributed modeling approach is a prerequisite for this to work. Using this ambition to let the engineers work in the best suited domain-specific tool enables an efficient use of human capital, in the sense that a modeler can switch between development projects without having to switch or learn a new tool. So this is also so very important in this approach. As I mentioned, we do need mechanisms for efficient distributed credibility assessment, meaning credibility assessment as an umbrella term. To realize this, we need to use well-established interoperability mechanisms, standards such as Modelica, FMI, and SSP, which I will talk about in a little bit. And we need to have mechanisms to establish and communicating digital threads. As we are these large-scale simulators or products, we need to be able to declare them as test-worthy. So to make sure that these things are that we are compliant, we have a process that describes how a modeler should ready a model to be exported for integration in a simulator. This process, called Saab Handbook for Development of Simulation Models, is publicly available at the reference here at the bottom of this page. And at a very coarse level, the handbook describes the steps that you see here in this figure. First, we have a specification activity where we define the purpose of the model. We formulate a verification and validation plan, etc. Then we go into the actual model development, where we connect component models into a subsystem model. We do verification and validation. We get feedback to refine our specification, and once we're ready, we are exporting the model to a central model storage. Once in the central model storage, this model can be integrated in a simulator at whatever level. And at this very coarse way of describing the process, one could express the development of simulators in the same way as well as component models. So Jan mentioned FMI. FMI is very important in this workflow. FMI is a result of the EU finance research project Modelisar, as far as I know. And basically, FMI specifies a generic format for export of model executables, or so-called functional mockup units. This can be done in a few different ways. FMUs for co-simulation, where a numerical solver is incorporated into the model package, or as FMUs for model exchange, where the solving of the equations is left for the integrating tool. And it provides various means of protecting IP in different ways in terms of source code export, gray box, black box, etc. FMI also provides a standardized interface description in terms of an XML schema. So FMI targets this export step of exporting models for integration in simulators. But we had what I refer to as simulators on various different levels. And that is, for example, or one aspect that the system structure and parameterization standard addresses. So SSP is a portable zip file type format, just like FMI, that contains everything in quotation marks that is needed to execute such a simulator. Just to advertise the latest version of standard, SSP 2.0 has been released slightly less than a year ago. This latest version of the standard is primarily intended to keep up and address the FMI 3.0 functionality, but it also provides some nice mechanisms to support incremental development of simulators and architecting. So in SSP, we use 3 of the primary artifacts that SSP specifies. We use the system structure description file format, which captures simulation architecture, how one model is connected causally to another model. The system structure values file format, which is a container for parameter values, and the system structure mappings format, which is a file format that allows you to have customization in the mapping of between values and the model components. Okay, so with that background, I leave the word to you, Jörg.
Yes, thanks very much. You can hear me?
Yes.
Perfect. Well, Robert explained to you a little bit the workflow which we have at Saab in our modeling and simulation development process. I will make now a step back to the very bottom and give you an example for this, how a very component model can look like. For that model, what I will present you, this is an flight mechanic model, which we are at the moment developing. And so the model which we have at the moment is a 2-DOF model. 2-DOF is for 2 degrees of freedom. However, that will be only the start. We are continuing to developing more models, 3-DOF up to 6-DOF. And that's basically for having a certain modularity in the future to choose a model in a adequate complexity for our later simulators. So, like I said, a 2-DOF model at the moment, 6-DOF model will be developed a little bit later on. And these models have as main task actually to provide the simulators and the other subsystems within the simulators with somehow realistic boundary conditions. So if we go forward, please, Robert. Next slide. Yes. So we are working at our department, like I said, like Robert mentioned already, with system simulations. However, what he didn't mention is that our focus is very much also on conceptual design of this subsystems. And here we are working very tight with our colleagues from the aircraft conceptual design department. And why I mention this, so they are actually designing, you can say, the outer part, while we are designing the what means this? When we are looking to military aircraft, you see
Jörg, you're cutting. We lost your audio. Can you hear us?
Hello, Jörg.
We are not hearing Jörg, Robert.
Should
That's
I?
actually what we try to achieve with this model. So what we are doing is we're building up.
There we go.
Was I away?
We lost you for a little bit, Jörg.
Okay, sorry. I so as I said, very short, we are working together with our colleagues from the aircraft conceptual design department, and aircraft conceptual design with the military aircraft design is very much is quite wide. We have different shapes, we have different control systems. So compared to civil aircrafts, we have a much larger variety. So that means also our models have to be more flexible, and by that we need a very modular approach. So if you can please continue with the next slide. So what you see now is actually how the model is basically built up. I will not go into now all the details. So basically the model have like the most flight mechanic models, yeah, a flight mechanic component, flight control part, a model for this, an atmospheric model, an engine model, and an aerodynamic model. As I said, there's no time for going into each model in detail, but I will pick out two examples which shows you a little bit how we work at Saab, how we share data, and how we integrate actually that what Robert mentioned, how we share models within these simulators. So what you see here is an example for the aerodynamic model. So we have the SSP structure, which Robert explained already, where we can have within this SSP structure different design projects, project A, project B, and all these projects have actually the possibility to take information and models out from this resource file. So our aerodynamic data, in this case, are simulated using a panel code, and this data are at the moment CSV data files, which are then read into 2D tables, which are which we can find in the standard Modelica library. And this CSV files are then the input actually for our for the aerodynamic modeling. The aerodynamic data are, as I said, an important part for the flight mechanic model, and the flight mechanic model can then saved as an model, point MO model, or directly exported as an FMU for yeah, if you want to share it further to other simulators. So, like I said, we use in the moment as CSV files. However, we are aiming for the future to apply a more standard, standardized file format, and that's the SSV file. Good. So what we are doing here is, as you can see, we are trying to make use of this Modelica Association standards. If you can please continue, Robert. Yes. So here you can actually see that how we can use actually FMUs. So what you see, we have this SSP system structure and parameterization. So we have the flight mechanic model on the right side. No, sorry, on the left side, the other right. And on the right side, the engine model. So here, what we have in the moment, it's in the current model is a very, very simplified engine model. However, later we want to have maybe a model which is providing much more precise data, which is more detailed than what we have now. And what we can use here is actually, as you can see, we have the same approach on the engine side. So you can have different engine designs, engine design A and B, and they all use, all these models are using the same structure as we are doing with the flight mechanic model. What you can do is then you can use, for example, the engine file exported as an FMU in our flight mechanic model instead of the current model which we have implemented at the moment. So that's basically the idea, and that is hopefully giving you an idea how we create this modularity and how we want and can share files within this simulator which we're developing. Yes, and to the very left, some very first results, what we get out from the simulator at the moment. Yes, anything to add, Robert?
No, and I think we're a bit. I don't think we have so much time, so I can wrap up with a brief summary. So. Our goal with this presentation was to highlight the importance for us of Modelica, FMI, and SSP, and the Modelica tools, of course, supporting all these three standards, such as System Modeler. There are other standards that are very relevant, emerging quickly under the Modelica Association. For example, I mentioned the digital thread, and the SSP LS traceability specification is something that provides really nice mechanisms for this. We see that we can use System Modeler on a number of different system levels, so that is great. And also, last, what Jörg showed is a novel, from our perspective at least, and modular approach to modeling and simulation of flight mechanics. And the idea is that we really try to bridge the gap between aerodynamics and systems modeling. And our plan is to successfully verify and expand on this approach in both ongoing and upcoming R&D projects.